Welcome to the University of Texas at Austin. I'm Professor Brian Evans. This is a class on real-time digital signal processing. This is Lecture 6, Part 1, on infinite impulse response filters. Previously, we've covered sinusoidal generation, review of signals and systems, digital signal processor architecture, finite impulse response filters, and sampling and aliasing. So for Lecture 6, we have 4 parts. This is Part 1. So in the first part, we will cover many roles for filters and the Biquad filter structure. And then for Part 2, we'll cover direct form implementations. Part 3 will be stability and Z-transforms. And then Part 4 will be cascaded biquads and conclusion. So I covered this in Lecture 5, Part 1, and also summarize a little bit of this slide. So this is the many roles for filters. These are many applications that we have in filters, applying to measure data, offline data, embedded in a real-time system as well. So the first one is noise removal, and this is the case when the signal and the noise are in separate bands, or another way to think about it is we can get rid of the noise that's out of the particular frequency band of interest. I've assigned a problem on homework 3, this is problem 1, on looking at this and quantifying the improvement that's possible when filtering out out-of-band noise. So an example in communication systems is to apply a bandpass filter at both the transmitter output and the receiver input to suppress the noise that's out of or outside of the transmission band. This can be also used for any other application where we have a band of interest and the frequencies that fall outside of that are less important. This can happen in audio, and it can also happen in image and video processing. So in image and video processing, we're concerned either with low frequencies or mid frequencies, and we can remove noise at higher frequencies, especially with oversampling. And with audio, the same case is true. We can either basically remove high frequencies beyond what the auditory system can hear. A second application is analysis, synthesis, and compression. This is particularly useful in decomposing a complicated signal into frequency bands and then applying a different operation on each band as appropriate. So earlier on Lecture 5 slides, I gave you this following example. I'll give you another one today. So in Lecture 5 slides, Part 1, we talked about analyzing a complex signal, a regular signal, and breaking it into 2 bands. So we talked about taking a signal, x of n, that could have all frequencies in it, and we're going to break it into a low frequency band and a high frequency band. And there's some overlap between the bands. So in the first case, we'll start with taking the input signal and passing it through a low pass filter, and taking the same signal and passing it through a high pass filter. And this is analysis. This breaks now a signal into simpler or smaller bands. An example low-pass filter could be an averaging filter. So we could have an averaging filter, 2-tap, just for simplicity, but any low-pass filter will do. And for the high-pass filter, we could have a first-order difference. And we've talked about both of these before. So in the low-pass filter case, again, this is just for simplicity, we can do a 2-tap averaging filter, and for the high-pass filter, a 2-tap first-order difference, but again, any low-pass and high-pass filter will generally do here. So let's talk about, okay, so that's the analysis part. So now I have 2 signals. I have x naught of n, and I have x1. So I have a high pass, x1 of n, and a low pass signal, x naught of n. Now for compression, I could put more bits. Let's say if the low frequencies were more important, I could now compress x naught and put more bits into the low frequency channel and fewer bits in the high frequency channel. I could also apply a different gain here to boost one band over the other. So if it were audio, I might want to boost the low frequencies if I want to hear more bass, or I might want to boost the high frequencies if I want to hear more treble. Now, after we've done this analysis, we'd like to be able, in many cases, not in all cases, but in many cases, to combine whatever we've separated back into one signal. Now, for this particular case, we can do it quite easily without an additional filtering step. More generally, we would apply a low-pass filter, again in the synthesis bank of filters, and a high-pass filter, again in the synthesis bank. So here we have a bank of 2 filters that does the analysis for us. It turns out we can do something very simple here to combine x0 of n and x1 of n back to a signal, back to one signal that has all frequencies in it. And what we can really do here is just simply add the 2 results to get back to a delayed version, really, of x of n. Or we could even subtract the 2 results, and that also works pretty well. Okay, so let's look at what that has. So if we look at the impulse response here, so I have a filter H0, and I have a filter H1, and we know from previous discussions that H0 is just a 2-tap averaging filter, so it's going to be, in terms of an impulse response, it's 1/2 of the discrete time impulse plus 1/2 of the discrete time impulse delayed by one sample. The first order difference, if we normalize it, is very similar, except that the plus sign becomes a minus sign. So now I have 1/2 of the discrete time impulse of n minus 1/2 of the discrete time impulse delayed by one sample. Now, if it turns out if we add the 2, if we don't have any filtering or any other operations in these low pass and high pass channels, then we can simply add the results of the low pass and high pass channel to recover the original signal x of n. And you can see that in that, now if I draw the bounding box here to represent my system that's a single input, single output system, all right, so there's my, now a single input and the single output we can just call y of n. And again, provided that we have a linear time invariant system here, which means that initial conditions in both the low-pass and high-pass filters are 0, which means to say that the initial value of the previous input for the low-pass filter and the previous input for the high-pass filter is set to 0. All right, so, and that's what enables us to talk about impulse responses anyway. We need to have an LTI system, and initial conditions must be 0 to satisfy the property of linearity and time invariance. So for this LTI system now, we can look at the input-output relationship. And what happens is the impulse responses will add, and if you add the 2 together, take H1 of n plus H1 of n, we get nothing but the discrete time impulse. The versions that were the shifted by 1 subtract out. Now we can also get away with subtracting the 2 if we wished. We can subtract H1 we say H1 of n minus H0 of n, and that also will give us, sorry, when H0 of n minus H1 of n, and that also will give us a discrete time impulse but delayed by one sample. So anyway, so this is a very simple way to recover or recombine the 2 channels, low pass and high pass, into one signal that's of all discrete time frequencies. Another example that's out there is in audio, which is to decompose an audio signal for playback over speakers into a subwoofer, a woofer, and a tweeter band. So we have 3 bands of interest, and you could use more, you could use 5. But here's a way to do it in 3, just for simplicity. So we could take, again, a signal, an audio signal that comes in, and I'll just do it, you can do it in discrete time or continuous time, as the format may dictate. If you're in a speaker, probably continuous time analog. So what we can do here is take take a signal. I'll go ahead and do a continuous time, it's fine. And we can break it into 3 filters, or break it into 3 channels. So now I have 3 bandpass filters. I have bandpass filter number, we'll call it 0, bandpass filter number 1, and bandpass filter number 2. And the job here, and we can do this also just as easily in discrete time. We could have sampled x of t and converted this in discrete time. And now what I'd like to have is I'd like to have the first bandpass filter pass frequencies from 20 to 200 hertz. This would be the very lowest frequencies in the normal audible range. Take the next bandpass filter and let that have from 200 to 2,000 hertz. And the last one would be 2,000 to 20,000. So the last bandpass filter number 2, would cover frequencies at the high end of the audible range for normal hearing. Okay, so this now, in the notion here, tweeter and woofer, a woofer is simply chosen because that's a deep sound that a wolf might make, and the tweet or tweeter sound is a higher frequency sound that a bird might make. So again, from the animal kingdom or animal world. All right, so we have woofer and tweeter, and then within the woofer frequencies, we have the subwoofer, which is the very deep bass in the audio. So these would go to 3 different speakers: the subwoofer, the woofer, and the tweeter appropriately. Now you could do, again, you could have more than 3 here in your speaker box. Not just, you could have 5, you could have 2. But anyway, the decomposition is, again, to get us in the right range to then feed. Now we can apply, one of the reasons we do this decomposition, there are 2 reasons. One is we can apply a different power amplification on each band of frequencies. And second, if we design this right, we can have, if we design the filters just right, we can get their impulse responses to actually add up to 1. Okay, so that'd be great that if we look at the sum of these 3 frequency bandpass filters, we get the sum of those 3 bandpass filters in terms of frequency response gives us a flat or all-pass response over the audible range for normal hearing from 20 hertz to 20 kilohertz. Again, this is an example of analysis. And the previous example was both analysis and synthesis. And so we had analysis for the bank of the low-pass and high-pass filters here in the first example, and the synthesis was simply an addition of the 2 channels. Okay, so we'll see this play out in a lot of different ways throughout the class. The last one is spectral shaping, and we really won't get to that until later in the lectures, and for us, it's be after spring break here at University of Texas at Austin, but lots of different examples we're going to cover for both a data conversion for A to D and D to A converters, and also for some communication system examples in channel equalization, which is to compensate for the frequency distortion in a communication channel, and also the analog front ends in a communication system. That's done in the receiver. But there are lots of different filtering that we have to do, and some of these are fixed filters that you've seen in the 2 examples that I've shown here on analysis. Both set of filters are fixed. They're not adaptive. Later on, we'll talk about adaptive filters in doing channel equalization and timing recovery, and also carrier frequency and phase recovery. So in those later cases, the coefficients of the filters will vary with time. Okay, so let's take a very simple, now let's move on into what I had on the previous slide was generally useful, whether we are going to have FIR or IR filters. And in fact, the 2 examples I had earlier, last slide, was the analysis with the 2-channel analysis were FIR filters, and then the audio example with the 3 channels of bandpass filters are probably going to be done as infinite impulse response filters in continuous time analog, but could also be done as infinite impulse response filters in discrete time and digital. So let's talk about infinite impulse response filters. So an infinite impulse response filter has an impulse response that is infinite in duration. So the impulse response goes from some start point to infinity. And a start point for us is typically 0. So here's an example impulse response that goes for all time from n equals 0 to n equals infinity. And it's a very simple decaying sequence of 1/2, 1/2, sorry, 1/2. So it starts at 1, goes 1/2, and then 1/4. So if I were to plot h of n, it would be a decaying exponential sequence of 1, then 1/2, 1/4, and so forth. So we get this gradual decline, but it doesn't hit 0 until infinity. And it's 0 before 0 in amplitude. Okay. So in this case, we have, again, a decaying exponential sequence. It starts at 0, which is enforced again by multiplying by the step function u of n. If we were to take the z-transform, take the signal and put it directly into the z-transform formula, we sum over n from minus infinity to infinity, but because we multiply by the step function, we only have to sum from 0 to infinity inclusive. We don't have to start back at minus infinity. The values of h of n are 0 for n equals minus infinity until n equals 1. We can now look at the remaining part of this summation, and we can put this under the same base. So we have 1/2 to the n times z to the minus n. This can be put over the same base because n is an integer. And that base is going to be 1 over 2z. So right now we have a base that's 1 over 2z. And that base is raised to the nth power. So in order for this summation to converge to an answer, the base has to be less than 1 in absolute value. And the absolute value is important. Z is complex, has a real imaginary components. So I get convergence here if the base is less than 1 in absolute value. Now, this also leads to the region of convergence. We can multiply both sides of the inequality by absolute value of z, provided z is not 0, and we can get the region of convergence. So this means that the absolute value of z is greater than 1/2. This is the area of the z-transform, or the z-domain, that's outside of a circle of radius 1/2. All right, so this is our transfer function. It's 1 over 1 minus 1/2 z to the minus 1. You can read the pole location directly from the transfer function. The pole location is when z equals 1/2. When z equals 1/2, the denominator in the transfer function goes to 0. We have to exclude that in the region of convergence, and we do, because the region of convergence is the absolute value of z greater than 1/2. So this is a fine impulse response. We'll see a little bit later, it's a mild low-pass filter. What we'll see, though, is if we have a transfer function, how do we implement this by computer? How do we apply it to an input signal? So if we let x of k be the input signal, or x of n actually probably is to be more consistent here, let x of n be the input signal and y of n be the output signal, then we can do the following to get the difference equation, starting with the transfer function. So the transfer function is simply in the z-domain, the ratio of the output z-transform to the input z-transform. It's also equal to the z-transform of the impulse response, and we've just computed that transfer function. And again, the transfer function assumes a linear time invariant system for this to make sense, to get the ratio of the output z-transform over the input z-transform. If the initial conditions were not 0, we could not get this ratio. So we multiply both sides by x of z, and we get a very familiar form that the output z-transform is the input z-transform multiplied by the transfer function of the LTI system. We can now substitute in h of z, capital H of z directly, into the formula, and now we're very close to the final answer. We can multiply both sides by the denominator, 1 minus 1/2 z to the minus 1. Multiply left and right. So on the right-hand side, we simply get x of z. On the left-hand side, we get the quantity 1 minus 1/2 z to the minus 1 times capital Y of z. Now we can take the inverse z transform, and we can get the difference equation. The inverse Z transform, I can take the inverse Z transform of capital X of Z, that gives me a little x of n. Take the inverse Z transform of capital Y of Z, this gives me y of n. The inverse Z transform of a subtraction is just a subtraction. If I scale the Z transform, I scale the time domain. The Z transform is itself a linear transform. Multiplying by Z to the minus 1 means I have a delay by 1 in the time domain, discrete time domain. And the inverse Z transform capital Y of Z is little y of n. So my difference equation now is simply y of n minus 1/2 y of n minus 1 equal x of n. So it's just the current output sample, excuse me, minus 1/2 of the previous output sample is equal to the current input sample. So to make this a difference equation that we can use to compute an answer, the output at any particular point in time, y of n, is now simply 1/2 of the previous output plus the current input, x of n. So as long as we have the initial condition for y, that is to say y of minus 1, and I know the input signal, x of n, then I can compute the output given this very simple difference equation. Simply with one multiplication and one subtraction, I can compute each output sample. So I can apply this to any signal that is one-dimensional. Let's make it a little more complicated. Let's go with a second-order system. So I now have dependence on the previous output, y of n minus 1, and the output from 2 samples ago. So here's y of n minus 1, here's y of n minus 2. And I'm still going to process the input, the current input value, x of n. So now my difference equation is the current output value is 1/2 of the previous output value plus 1/8 of the output 2 samples ago plus the current input signal sample value. We can still do recursive computation on this. I now need 2 initial conditions, y of minus 1 and y of minus 2. For the filter to be linear and time invariant, a necessary condition here is the initial conditions must be 0. So we have to make sure that they're set to 0. And again, these initial conditions correspond to the delay blocks in the block diagram. We'll get to that in just a second. The transfer function is, again, we got to find the impulse response, or we can just take the Z transform of the difference equation and factor it into a transfer function. And again, this works because the initial conditions are 0. Okay, so if we take the Z transform of the difference equation, little y of n becomes capital Y of Z, that's just a placeholder. 1/2 times little y of n minus 1 becomes 1/2 times Z to the minus 1 times y of Z. Next term, so if I do the Z transform of the next term, it's 1/8. The 1/8 comes down. Delayed by 2 means I multiply by Z to the minus 2. And then the Z transform of little y of n is capital Y of Z. And then finally, we have a placeholder. The Z transform of little x of n is capital X of Z. I can now, again, same thing as I did last time, I can factor out the common terms of y. So what I can do is move, in this case, I'll move the common terms of capital Y of Z to the left-hand side, factor out capital Y of Z, and that factor gives us, if we move the 2 terms here to the left-hand side of the equation, and I factor out capital Y of Z, that polynomial is what we see here in the denominator, 1 minus 1/2 Z to the minus 1 minus 1/2 Z to the minus 2. I then divide both sides by that polynomial, and also divide both sides by capital X of Z, and I get the transfer function, capital H of Z. It's a second-order system. I have 2 roots in the denominator, so those roots are the poles. I also have some trivial zeros at the origin, and I can see that by multiplying numerator and denominator by Z squared, and I end up with a Z squared term in the numerator. I have two zeros at the origin. If I look at the pole values, we're going to find out very quickly in the next lecture, the next part, lecture 6, part 2, that these poles are not terribly, they're not going to give us the world's greatest filter. It'll be mildly low pass, but not a great response. There are much better filters out there. But again, this example is chosen for the simplicity of the coefficients of 1/2 and 1/8. Okay, so here we have a second-order system, 2 poles, and 2 trivial zeros. And here's a block diagram representation. To find the block diagram representation, the way I do it is start with x of n, my current input, assume that I have the current output, and start connecting the dots. So in order to compute the difference equation, I need to know the previous output, which I can obtain from the current output, assuming I have it, or I had it, by simply placing a delay by 1 sample block in the picture. And to get the output from 2 samples ago, I simply have to take the previous output and apply another delay block. Then from each output of each delay block, I have to scale by the appropriate value for the difference equation. So I have 1/2 of y to the n minus 1, and then I have 1/8 times y of n minus 2. So I bring those 2 results of the multiplication to the summation node, and I add to those 2 terms the current input value x of n, and I'm left with now the output is simply y of n. I just have to now draw the arrow to connect to the output y of n. And that's it. So the block diagram is really useful when you're dealing with a complicated system with lots of different subsystems. We can use hierarchy and modularity to capture the relationships in the subsystems to the parent systems, until we're finally to the overall top-level system in our hierarchical block diagram. The alternative is to maintain hundreds or even thousands or tens of thousands of equations, and it's hard to know how they relate. So just like we use modularity and hierarchy in software in doing our high-level language source code development, we can use hierarchy and modularity in representing the system in block diagram form. Okay, so this is known as a biquad. This is a second-order filter section, which means a biquad here is short for biquadratic. Biquadratic means a ratio of 2 second-order polynomials or quadratic polynomials. I have 2 poles, and I'm going to say 0 zeros here. Now you can also argue that I have 2 trivial zeros at the origin, and you'd be correct as well. The zeros at the origin do not affect our magnitude response, and have very little effect on the phase response. It does not change whether the phase is linear or not. Okay, so anyways, this is a biquad. We call this an all-pole filter. So it's an all-pole filter. That is to say we have only poles that are of interest. Yes, we have 2 trivial zeros. Those are not terribly interesting, but anyway, this is an all-pole filter, and we'll call this with 2 poles and 0 zeros that matter. We'll need this on the next slide. Okay, so this is an example of feedback, second-order system. All right, so let's talk about the discrete time biquad. Now we can generalize. The biquad here to have 2 non-trivial zeros in addition to 2 non-trivial poles. So here we're going to let the biquad have 2 poles and 0, 1, or 2 non-trivial zeros. So if we want to correct this, it really is non-trivial. Non-trivial zeros. Okay, so here is one of many possible block diagrams for a biquad of this form. And it looks like a lot's going on, so we'll come back to this in just a second and do the analysis in the z domain. But let's go right to the transfer function. So the transfer function is a ratio of 2 quadratics. And this is, again, we have some interesting things here. So if we look at the roots of the numerator, and we know that, well, our coefficients here for implementation, B0, B1, and B2 will be real valued. And the reason for this is that our signal x of n will be real valued, excuse me, and that the y of n will be real valued. So our filtering here will be real valued. Now there's some exceptions to this in practice, but by and large our coefficients are real valued. So for the case of real valued coefficients, we're going to get 0 locations that are either real valued, and they don't have to be the same real value, or they can be conjugate, or they have to be conjugate symmetric. One choices that we have. For the denominator polynomial, the roots of that polynomial are in the same way, either conjugate symmetric or they are real valued. And we saw an example of that on the previous slide where we had two poles and both were real valued, if you remember. So we go back one slide. So here's a case of, this is a second order section, again with 0 non-trivial zeros and two poles. And we had two pole locations. Both are real valued and they were not equal to each other. They could be equal to each other, but they don't have to be. And there they were not. Okay, so now this is our second order section, and a couple interesting things here that, again, B0, B1, B2, and A1 and A2 are all real valued. You'll notice that there is no A0 separately mentioned. The A0 here is typically normalized to B1. All right, so let's see if we can derive this transfer function from the block diagram. And the way we're going to do it is we're going to do divide and conquer. We're going to break this into two simpler systems, analyze them separately, and then combine the result to get the final transfer function. If you notice on the block diagram, I have input signal x of n and output signal y of n. That's not a surprise. But in the middle, I have the signal v of n. So I have an intermediate signal v of n, and I can get there by really applying a filter from x of n to v of n, and I can get from v of n to y of n by applying another filter. So as a block diagram, I have x of n coming in. This goes through an LTI system to give me v. V goes through another LTI system to give me y. Now the system that goes from v to y is something very familiar to us from previous lectures, and this is just a finite impulse response filter. So if we look down from v of n, the term here after the delay block is v of n minus 1. And we have v of n minus 2. Excuse me, to go to y of n, I'm going to now use from v of n to y of n, this is now just a feed-forward filtering. And if we look at the structure, this is nothing but the tap delay line, but I have the delay blocks vertically instead of horizontally. But the flow is feed-forward. There's no feedback from v of n to y of n. So if we look at the difference equation relating y and v, we get something very familiar. We get y of n is b0 v of n plus b1 v of n minus 1 plus b2 v of n minus 2. This is nothing but an FIR filter, and the transfer function is going to be a polynomial in non-negative powers of z. So if we look at the transfer function for h naught, all right, so h naught is just going to be one plus b1 z to the minus 1 plus b2, well, I missed b naught here, sorry, b2 z to the minus 2 so we have b naught plus b1 times z to the minus 1 plus b2 times z to the minus 2. So it's an FIR filter. This is h1, I'm sorry, h1. That's h1 of z. Right, that's the route from v of n to y of n. Okay, now, if you look at the left half of this biquad, it's nothing but feedback. I have v of n. So now if I look at the input x of n, and v of n now is the output, we're going to look at the left side here. So now v of n flows back to x. And if you look at this, this is exactly the block diagram I had on the previous slide this left half of the biquad filter structure is the all-pole section. It's the feedback section, and it's just like the filter on the previous slide. So in the previous slide, again, if you remember, we had exactly these terms. This is exactly the left-hand part of the biquad, except that now this 1/2 is really A1, and the 1/8 is really A2. So that's A1, and that's A2 more generally in the biquad. Okay. So now again, back to our discrete time IIR biquad. Again, I have two sections. I can decompose this into two parts. An all-pole section for H0 of n and an all-zero section for H1 of n. In other words, I have an all-pole filter for H0 of n, and I have an FIR filter for H1 of n. And the cascade here works fine. I have a cascade of two LTI systems, so assuming that they're LTI and that I have exact precision, so if I have a cascade of two LTI systems, then the resulting transfer function from x to y is simply the product of the transfer function for H0 times the transfer function of H1. And so that's shown here algebraically in the bottom half of the slide. So again, the overall transfer function, capital Y of z over capital X of z, is the transfer function of v over x, which is, again, this is the all-pole part, times the transfer function of y over v, which is the FIR part. Okay, and you can kind of see that now in the transfer function for the overall biquad. Again, I have the numerator polynomial, which is the FIR part, and I have the denominator, which is the all-pole part. Now, if I set, I can get the first order section out of this if I set B2 to 0 and A2 to 0. And now I'm down to a first order section, which is also a building block. So the reason we do the biquad is that this is a fundamental building block for implementing infinite impulse response filters. We'll use cascades or parallel combinations of biquads. Cascades probably a little more common, to implement a complicated or higher order transfer function. And we'll see why that's important a little bit later. But it's a lot easier than using a very big filter that just implements the entire difference equation with just one tap delay line or two just in one shot. That has some numerical issues that we'll talk about a little bit later. Okay. So we'll pick up here with a lecture 6-7 slide for part 2. This ends lecture 6, part 1. And thank you for joining us.